Hariom children. So in the last classes we were seeing about ray optics. We have completed the entire topic and I have given you a test also regarding this. We had discussed many problems, many MCQ questions. Hope this chapter is thorough by now. Now we'll go into the next topic, that is wave optics. As the name suggests, wave optics, light travels in the form of waves. Ray optics, light travels in the form of rays. Here, light travels in the form of waves. Now, there were many theories regarding the nature of light. First one was given by Newton in his corpuscular theory. That's called as Newton's corpuscular theory. According to this theory, light consists of small particles called as corpuscles. But this theory was not accepted because it couldn't explain the simple phenomena like reflection, refraction, etc. According to corpuscular theory, the velocity of light is greater in a denser medium compared to a rarer medium. But this was proved false. As we all know, we finished studying refraction, everything we know. Next is Huygens wave theory, which means light travels in the form of waves, and this is what we are going to see now. Next came what is called as Maxwell's electromagnetic wave theory. According to this theory, light is an electromagnetic wave. That is, it consists of an electric field vector, magnetic field vector, perpendicular to each other and perpendicular to the direction of propagation. That is, Maxwell proved that light is transverse in nature. Next came called as quantum theory. According to the quantum theory, light is given in the form of small packets of energy, which is called as quanta or photon. This was given by Planck. So it is called as Planck's quantum theory, and later on Einstein used this Planck's quantum theory to describe photoelectric effect, for which he was awarded the Nobel Prize also. Now, after this came dual nature of matter, which was given by de Broglie. That is, light can exist in the form of waves. It can also exist in the form of particles. That is, dual nature of matter. This was given by de Broglie. So, all this we'll study in our next unit. Now, we'll go to what is called as Huygens wave theory by a scientist. He was a Dutch scientist, Christian Huygens. In 1678, came out with this Huygens wave theory. That is, light travels in the form of waves. We know what is a wave. A wave motion is a disturbance which travels through a medium due to the repeated periodic motion of the particles of the medium about the mean position, the motion being handed over from one point to another. This is what we studied last year. So we know how you get wave, which means that for the propagation of a wave, a medium is necessary. Now, if you take a stone and if you drop it in a pond, you will be able to observe ripples. Ripples are nothing but alternate crest and trough. What is crest? Crest is a portion of the medium which is highly raised above the normal position of rest, and trough is the portion of the medium which is highly depressed below the normal position of rest. If you see the particles of the crest, all the particles of the crust will be in the same state of vibration. or we say that they are in phase. Similarly, all the particles in the trough are in the same state of vibration and we say they are in phase. Now, the locus of all these particles which are vibrating in phase or which is in the same state of vibration is what is called as a wavefront. Is called as a wavefront. So, Huygens was the first to introduce this concept of wavefront. According to Huygens, each source gives out light which spreads in all directions in the form of waves in a hypothetical medium called as ether. Hypothetical medium is nothing but an imaginary medium. So in this, we need a medium because last year we studied that for the propagation of a wave, a medium is required. That is why this ether medium was considered. This ether medium is pervading all space. So last year we had already studied about the velocity of a wave. What is the expression for the velocity of a wave? V is equal to root of eta by rho. Rho is the density of that medium and eta is the elasticity, which means that the density here in this case, Huygens assumed that the density of the ether particles is very small and the elasticity is very high, as a result of which the velocity of light is also tremendous. So we know what is the velocity of the light. How much is it? It is 3 into 10 power 8 meters per second. So high velocity of light is possible only if you consider the density to be small and the elasticity of the medium to be very high. So what did Huygens say? Light is propagated in the form of waves. Now I told you when a body is dropped in a pond, you observe ripples. Similarly, if you consider light source, if you consider a point source of light, this point source of light sends out disturbances in all possible directions. Sends out disturbances in all possible directions. And at any instant of time, this is the source of light. At any instant of time, if you consider at any particular distance from the center, all the particles which are equidistant from the center will be in the same state of vibration or they will be in phase. Now, if you join all these particles of the medium or all the points over here, they lie on the surface of a circle if it is 2-dimensional. And they lie on the surface of a sphere if it is 3-dimensional. Accordingly, the locus of all the particles which are equidistant from the point source and which are vibrating in phase when the disturbance reaches them is called as a wavefront. So what is a wavefront? It is the locus of all the particles equidistant from the point source vibrating in phase when the disturbance reaches them. That is called as a wavefront. Now, depending upon the shape of the source, you have different types of wavefront. When a point source is used, we get what is called as a spherical wavefront. This is what is called as a spherical wavefront. When a linear source is used, what can be the shape? You can easily guess it. What is a wavefront? It is the locus of all the particles which are vibrating in phase when the disturbance reaches them. So when you consider a linear source, you can see that the light from this linear source will go in all possible directions. and at any particular instant of time, all the particles which are equidistant from the linear source, they lie on the surface of a cylinder, and such a wavefront is called as a cylindrical wavefront. Is called as a cylindrical wavefront. So to get the cylindrical wavefront, you consider a linear source. Light is traveling in all directions, and you can see that this is a cylindrical wavefront. You can see that. The envelope of all the points lie on the surface of a cylinder. Such a wavefront is called as a cylindrical wavefront. Now, as the spherical wavefront advances, see, this is the point source, and you are able to see this is the portion of a spherical wavefront. As the spherical wavefront advances, its curvature goes on decreasing, and finally, at a very large distance from the source, it appears plane, and such a wavefront is called as a plane wavefront. Is called as a plane wavefront. See, the light coming from the sun, by the time it reaches earth, see, sun is spherical in nature. It is a point source, and around that point source you have spherical wavefronts. By the time the sun's light reaches the earth, it becomes plane. Such a wavefront is called as a plane wavefront. So how do you get a plane wavefront? When you consider the source to be at infinity. How do you get a cylindrical wavefront? When you consider a linear source. How do you get a spherical wavefront? If you consider the point source. Point source, spherical wavefront. Linear source, cylindrical wavefront. When the source is at infinity, you get a plane wavefront. Whatever it is, whether it is a plane wavefront or spherical wavefront or cylindrical wavefront. Suppose if you consider this to be the portion of a plane wavefront, the rays are always normal to the wavefront. Whether it is here or whether it is here or whether it is here, the rays are always normal to the wavefront. Now, you have two types of spherical wavefront. One is called as this. Suppose if light is diverging from this point, the wavefront is called as divergent spherical wavefront. It is called as divergent spherical wavefront. Suppose if light is converging to a point, then it is called as convergent spherical wavefront. This is convergent spherical wavefront, and this is divergent spherical wavefront. This is the introduction.